Okay, let's talk about evaluating limits. So we're going to evaluate limits at just regular numbers like 0 and 3, and later on in the video we're going to evaluate limits at infinity. First, let's start off with this. You might try to use direct substitution here, and in this case, if you substitute x for 6 here, then you're going to get a number over 0, and we don't want that. So what we're going to do instead is realize that 216 is actually equal to 6 cubed. So knowing that, we can factor it out. Start off with the cube root of the first number, and then the cube root of the second number, then the cube root squared, minus both cube roots multiplied. Actually, this is plus. And then plus the cube root squared, 36. So if you want to factor the difference of cubes or sum of cubes, just remember for the signs here, you're going to be following something called SOAP. Same, opposite, always positive. So just remember that. So the first one here, this is negative because it's the same. The second one is positive because it's the opposite. And third one's always positive. Okay, this is all over x minus 6. So here we can actually cancel these out. And then you're going to be left with just x squared plus 6x plus 36. So now you can substitute in 6 for x, and we're going to get 6 squared plus 6 times 6 plus 36, which is equal to 108. So that's your answer. Okay, next problem. Okay, same thing here. It looks like we got the sum of cubes instead of difference of cubes this time. So we can also factor that. So it's the cube root, the first number, cube root of the second number, and then it's squared, and the product of the two, and then the second number squared, 16. And SOAP, same, opposite, always positive. Divided by x plus 4. These two cancel out. So we're left with x squared minus 4x plus 16. And then we can substitute in 3 for x. So you get 3 squared minus 4 times 3 plus 16. So it's going to be 9 minus 12 plus 16, which equals 13. So this one, if you were to substitute in 0 for x, you're just going to get a number over 0, which is undefined. So let's multiply it by the conjugate, root x plus 1, and we're going to divide that by the same thing. So we're technically just multiplying it by 1. Okay, let's multiply this out. Root x plus 1 squared is just x plus 1. 1 times negative 1 is negative 1. We can distribute the x in here. So plus x here. Plus 1 minus 1 cancels out. So notice how there's an x in every single variable here. We can just divide that out. So you get 1 over x plus 1 plus 1. Distribute in 0 for x. You get 1 over 0 plus 1 plus 1, which is equal to 1 over root 1 plus 1, which is equal to 1 over 1 plus 1, which is equal to 1 over 2. So that's your final answer, 1 over 2. This is the final problem before we move on to limits at infinity. Okay, so we can't distribute in the 0, and we have roots here. We can just multiply it by the conjugate here. So root x plus 2 plus root 2 all over root x plus 2 plus root 2. So it's x plus 2 minus 2, and distribute in the x plus x root 2. Actually, we don't need the parentheses here. Plus 2 minus 2 cancels out. Again, in each variable here we have an x, so we can divide out the x. 1 over x plus 2 plus root 2. Now we can substitute in 0 for x, so we're going to get 1 over 0 plus 2 plus root 2 equals 1 over root 2 plus root 2, which equals 1 over 2 root 2. And obviously we can't leave a root in the denominator, so we're going to multiply it by root 2 over 2. Root 2 over root 2. And we're going to get root 2 over 2 times 2, which equals root 2 over 4. So that's the final answer. Okay, moving on to limits at infinity. Let's say that we have limit of 1 over x as x approaches infinity. So as x approaches infinity, x is going to get larger and larger and larger. So as the denominator of a number gets larger and larger, the actual number is going to get smaller and smaller. So let's say like 1 over 2 is only equal to 0.5. But if you were to do like 1 over like 1,000, that's equal to what, 0.001. It gets smaller and smaller as the denominator gets bigger and bigger. So because here x is approaching infinity, so the denominator is going to get infinitely bigger. So that just means that it's just equal to 0. Because you're approaching 0. As the denominator gets bigger and bigger, it's never going to reach 0. 1 over anything can never be 0, but it's going to get closer to 0. And if you want like a graph approach, 1 over x kind of looks like this. You see, as x approaches infinity, it goes here infinitely. The y value is going down and down, but it's never going to ever touch 0. It's just getting closer to 0. Okay, let's do this one. So, turns out if you have something like this, you can actually distribute the limit into both of these numbers. So let's write that out. So it's going to be a limit of 7 as x approaches infinity, plus limit of 1 over x cubed as x approaches infinity. Okay, we can evaluate these each separately. You see that this here is a constant. There's no x in there. It's just a constant. So that means that the graph just stays at like 7 this entire time. Okay, it's like this. It's a constant graph. It is a horizontal line, y equals 7. So as x approaches infinity, it goes here. It's just going to stay at 7 forever. So the limit is 7. Now for this next one, you see x is in the denominator and x is approaching infinity. So it's going to get bigger and bigger infinitely. So it's approaching 0, but it never reaches 0. It's approaching 0. So 7 plus 0 equals 7. So the answer is 7. Okay, so when it comes to limits at infinity, there is actually a general rule that you can follow. So let's say that f of x is equal to like number a to the nth power over number b to the d power. So it turns out that when the degree of the numerator is smaller than the degree of the denominator, the limit equals 0. So an example like that would be limit as x approaches infinity of x over x cubed. You see here that the exponent, the degree of the denominator, you see here that the degree of the denominator is bigger than the degree of the numerator. The degree of the numerator is 1, and the degree of the denominator is 3. So denominator is bigger. So even though x is approaching infinity on the top and bottom, the bottom is approaching a bigger number faster because it's cubed. So that means that the denominator is always going to be a lot bigger than the numerator. So it's approaching 0. So that's why this is how it is. The next one, what if the degree of the numerator is equal to the degree of the denominator? So that's going to look something like this. We have like 7x cubed over 6x cubed. Squared. You see the degree here is the same. So when the degree is the same, we're going to look at the leading coefficients, 7 and 6. Because the degree is the same, they're always increasing at the same rate because they have the same degree. Here, they have a different degree. The denominator has a bigger degree. So that's why the denominator is growing faster than the numerator. But here, both sides are growing equally. So the ratio between them is actually the ratio between the leading coefficients in front of them. So the limit is actually 7 over 6. So when the degree of the numerator is equal to the degree of the denominator, the limit is equal to, actually let's smooth this over here. The limit is equal to the ratio of the leading coefficients. Okay, third one. What if the numerator, the degree of the numerator, is bigger than the denominator? You have x cubed over x. You see that the degree of the numerator is 3, the degree of the denominator is 1. So the numerator is growing bigger, it's growing faster than the denominator. So the number is getting bigger infinitely. So what does that mean? That means that the limit is equal to infinity, but that means that the limit doesn't exist, so D and E. So if the degree of the numerator is bigger than the degree of the denominator, then the limit does not exist. Okay, so really all you have to look at are these things right here. So I'm going to put these right here for you to reference, and we're going to do some practice problems. Okay, so what's going on here? We see that the degree of the numerator is 2, the degree of the denominator is 3. So which rule are we following here? We're going to follow the first one here. So that means that the limit is 0. It's that easy. We don't have to look at this because -2 in the grand scheme of things doesn't really do a lot. And 4 and 9 in the grand scheme of things doesn't do a lot either. What's really impacting the ratio between these two numbers, the numerator and the denominator, is the degree here. So that's all we look at. Let's look at this one. Again, we literally do not have to pay attention to these numbers. Let's look at the degree. We have 2 up here. Oh my god, why is it yellow? We have 2 up here. We have 1 up here. So what can we say? We can say the degree of the numerator is bigger than the degree of the denominator. So we're following this rule. So what does that mean? That means that the limit does not exist. D and E. Okay, final example for this video. Alright, I know this looks really long, it looks really tedious, but trust me, it's not that deep. So we don't have to look at this, because that's a constant, that's +1, that's not going to do anything. We only really have to pay attention to this right here, because this in the grand scheme of things doesn't really do a lot. Same with this and this. We're highlighting these two specifically in blue because these are what we're looking at. Why? Because the degree here is smaller than the degree here. The degree here and here is smaller than the degree here. So what's really important, what's really making an impact on the ratio as x is approaching infinity are these ones, because they're growing a lot faster than any of the other variables. So what do we notice? We notice that the degrees are the same. It's all to the 5th power. That means that we got to look at this middle rule. This middle rule right here, where n equals d. It means that the limit is the ratio of the leading coefficients. So the limit is 2/5, and it's that easy. That's the final answer. So yeah, that's it. Thank you so much for watching this video. I hope you learned something new, and I'll see you in the next one.